Hi, this is week 3 of AP Physics, and in today's lesson we're going to go over motion in one dimension as well as free-falling objects. So there's our agenda. Let's get started. Our objective: we will analyze experimental data describing the motion of an object and be able to express the results of the analysis using a narrative, mathematical, and graphical representation. So that's our goal. Alright. One-dimensional motion. When an object moves with constant acceleration, the instantaneous acceleration at any point in time interval is equal to the value of the average acceleration over the entire time interval. Therefore, average acceleration equals acceleration. Furthermore, the constant acceleration formula can be reconfigured to give us this formula right here, which I've also written on the board here as well. In this formula, the values are as follows. Vx will be the velocity after some time has gone by. Vo is velocity at time 0. A is the acceleration measured in meters per second, and t is time measured in seconds. Here I have them for the x-axis, which is why you see x in all of these guys, velocity in the x-axis here, there, and acceleration in the x-axis. Though some of the problems we'll be looking at, particularly in free fall, they're going to be on the y-axis, so those will be replaced by y's. Alright, another formula that we'll be using is this one as well. So the displacement of an object, so how far it goes from the origin, with constant acceleration can be calculated using this formula right there. A lot of the time we end up moving the x, that's our displacement, over on this side, and we just end up with delta x, just to make the formula a little bit smaller. And here we have x is a displacement in meters, xo is a displacement at time 0, vox is displacement on the x-axis after time 0, and ax is acceleration on the x-axis, and finally t is time in seconds as well. Another formula that is very handy to solve these problems is the velocity of an object. This formula right here, velocity squared is equal to original velocity squared plus 2 times the acceleration times the displacement of the object. So for this one, it says the velocity of an object with constant acceleration can be calculated using that formula. So velocity, so how quickly is our object moving? Alright, and the values are the same one more time. Delta x is the change in displacement. Alright, so let's go ahead and get to our first example. This is example 4. It refers to a race car. It says a race car started from rest and accelerates at a constant rate of 5 meters per second squared. Part A, what is the velocity of the car after it has traveled 30 meters? And part B, how much time has elapsed? And part C, calculate the average velocity of the vehicle. Alright, so let's go ahead and start with part A. In this one, we should start by writing down what is given to us. Given to us is that the car is starting from rest. So velocity at time 0 is 0 meters per second. Also given to us is the fact that we have an acceleration. So the acceleration on the x-axis, the car is flat, it's 5 meters per second squared. Next, they want to know what is the velocity of the car after it has traveled 3 meters. So our change in displacement is, 3 meters. So that's all the information that's given to us, and they want to know the velocity of the car, after 30 meters, I apologize. Okay, so now, what is the velocity of the car after 30 meters have gone by? Alright, so we have this formula on top, and to solve for the velocity, but we don't have the time, so we can't really use that one. Same problem with this one. That one, right here, we do have everything we need to solve for the velocity of the vehicle at that particular instant. Alright, so let's go ahead and get to work. Formula will be this. V squared equals VO squared plus 2 times A times change in displacement on the x-axis. All of these are on the x-axis. Now, this VO, it has a value of 0, so it has no value. So we can make the formula a little bit smaller. since it has no value. So it's just really 2 times acceleration times the displacement, which was 30 meters, and then we're going to have to square root it. So to get the answer, we would square root both sides, and the answer will be this. Alright, in the AP test, a lot of times they're not really looking for a numerical answer. What they want is, what formula would you use to solve for this? So the answer might be square root of 2 times a times x. And that will be your answer. You wouldn't put numerical values into it. Only about a quarter of the problems in the multiple choice section of the AP test have a numerical answer. For this problem though, they do want a numerical answer. So what is the value? Alright, so we're going to plug in the values. We're going to go ahead and solve for it. So 2 multiplied times the acceleration, which is 5 meters per second squared, multiplied times the 30 meters, which it traveled, multiply all of these values, then square root it, and that's going to go ahead and give us our answer. So that will be 30 times 5 times 2, that's 300, and then square root of 300, 17.3 meters per second. That is our velocity after we reach a 30 meter mark. Alright, that takes care of part A. Let's go ahead and move on to part B. For part B, they ask you guys, how much time has elapsed? Alright, so we want to know the amount of time it took. So I'm going to go ahead and solve for that. I'm going to leave the answer for part A here. The velocity after some time had gone by, it was 17.3 meters per second. Alright, so now let's move on to part B. And in part B, they want to know how much time did that take to go from 0 to 30 meters, accelerating at 5 meters per second squared. So let's see. We're going to go ahead and use this top formula. Why? It has time, we do have the acceleration, and we know the velocity initial and final. So we're going to use that formula. So let's write it down. Now, velocity initial is 0, so again, this is just going to cancel out. So we can simplify the formula a little bit. Now, if in an AP test you were to say, well, there you go, there's a formula, you would lose credit for that because right now you're solving for the velocity and they ask you to solve for the time. So as far as giving a formula, the time has to be isolated on one side of the equal sign before that's the actual answer. So we've got to go a step further. And here we go. There's our formula on the x-axis. Alright, so it's just the velocity divided by the acceleration. That will give you the amount of time it takes for this vehicle to reach that 30 meter mark. So let's plug in the values. Time is equal to velocity. Our velocity was 17.3 meters per second, and the acceleration was 5 meters per second squared. So as we divide both of those, we end up with 3.46. We can round it off to 3.5 seconds, and that will be our answer for part B. Alright, so there we have it, part B. Now part C, they're going to go ahead and ask you, calculate the average velocity. Now average is simply you get the initial velocity, final velocity, add them together, and divide it by 2. That's how you get an average. So the average velocity, so I'm going to put the V with a little symbol on top, is going to be the velocity initial plus the velocity after some time has gone by divided by 2 because it's an average. So that'll be our formula. So for our average velocity is 0 plus 17.3 meters per second over 2. So for part C, the average velocity will give us a value of 8.6 meters per second squared. That will be our average. Okay, that wraps up example number 4. Up next is example 5. In this problem, they ask you guys a typical jetliner and lands at a speed of 71.5 meters per second and decelerates at a rate of 4.5 meters per second squared. If the plane travels 1 second before beginning that deceleration, then what is the total displacement of the aircraft between touchdown and coming to rest? So they wanted to go the whole journey, including the 1 second when it touches down, and then a second goes by, then the acceleration begins, negative acceleration in this case. Alright, so a graph would help us visualize this problem a little bit more. So we're going to have a velocity time graph. So we're going to have t here and v here. And this plane comes in at a velocity of 71.5 meters per second. That's our velocity that is traveling at. Now, for time-wise, 1 second goes by, and then after 1 second, the brakes begin to be applied, and we get negative acceleration, the plane slowing down. How much time that takes is not given to us. Alright, so they want to know, though, how far did the plane travel? Alright, so I want to point out one thing. The first second from touchdown to 1 second, that amount of time, there's no acceleration because the brakes have not applied. So the plane maintains a constant speed. Alright, now from here to there is a negative acceleration of 4.5 meters per second squared. Okay, so what we're going to go ahead and do is we're going to go ahead and figure out how far that plane traveled. So let's go ahead and start with this section right here with the acceleration. That's what we're going to be solving for. How far did this plane actually travel on the x-axis? So we do have the initial velocity, we do have the final velocity because we know it's coming to rest, so it's going to stop, and we do have the acceleration. So we're going to go ahead and plug those together to go ahead and solve for our answer. So their formula is going to be this: v2 equals vo plus 2 acceleration and the displacement. And again, we're solving for the displacement for this region right here while there was negative acceleration. Alright, so I need to isolate this delta x, that's the displacement. So let's go ahead and do that. First of all, one of these guys is a 0, which is this right there. That is a 0. Why? Because the plane at the end of this problem has got a velocity of 0. So that's going to go away. So I'm going to put 0 right here. Next, I'm going to go ahead and move this, the original velocity over to this side. That's going to make it negative. And after that, I'm going to go ahead and get rid of the acceleration in the 2 by dividing by them. So that cancels them out. Now that gives me my answer, which is going to be negative VO, the original velocity, squared over 2 times the acceleration. And that's going to give me the displacement for that section right there. Alright, so for that section, let's go ahead and solve for that. Let's call this one section 1 and this one section 2. So I'm going to put delta x2 for that section. That's our second section right there. Alright, so it's going to be negative VO. Let me go ahead and put in the value for that. The plane was traveling at 71.5 meters per second. We're going to square that value. Now notice that the negative is outside of the square, so we're not squaring the negative. And then it's going to be at the denominator 2 times the acceleration. Now it is decelerating, it is slowing down, so though they wrote here 4.5, they do tell us that it's decelerating, so therefore it's negative acceleration. So it's negative 4.5 meters per second squared. Alright, so we plug into the calculator. I want to point out that that negative and that negative will end up canceling each other out. Alright, so in the calculator, 71.5 squared gives us 5,112, a bit of rounding off. 2 times 4.5 will give me 9, so 568 meters. That is how much it traveled while decelerating. Now, in part 1, what about from the time it touched down initially to the time it began to decelerate? How much time went by? Now, there's no acceleration there, so we can use a very simple formula for that. It's going to be velocity is equal to displacement over time. Okay, and we do have the time and we do have the initial velocity, so we're just going to go ahead and move it over here. So we end up with this formula. Velocity times time. Alright, so that will be for part 1, so I'm going to label that as such. Velocity was 71.5 meters per second, and it only lasted 1 second, so you multiply both of these to give us the first part of the journey, which is 71.5 meters per second. So to get the total journey, so I'm going to put delta x with a t for total. It would be the first part of the journey times this plus the second part of the journey. So the answer for that one would be 71.5 meters per second plus 568 meters per second. That gives us a grand total of, we're going to round it off a little bit to 640 meters. That would be the length that this plane would travel as it's slowing down to come to a full stop. Alright, 640 meters. Alright, that takes care of this problem. Our next problem is problem number 9. In this problem, they bring up a speedboat. It says the speedboat increases its speed uniformly from 20 meters per second to 30 meters per second in a distance of 200 meters. What is the acceleration of the speedboat? That's part A. And part B, find the time it takes the speedboat to travel the given distance. And part C, draw a velocity time graph for this problem. Alright, so let's start with part A. In part A, they want the acceleration of the boat. And I want to write down what is given to us. Given to us is the initial and final velocity of the boat. So at time 0, when we first started, the velocity was 20 meters per second. And after some time has gone by, it's 30 meters per second. Alright, the distance traveled by this boat, so it is displacement on the x-axis, it is 2.00 times 10 to the 2. If we move the decimal over twice, you'll recognize, oh, that's just 200 meters. Alright, so again in part A, what is the acceleration of the boat? We have the displacement, we have the initial and final velocity, so we're going to use this formula to solve for the acceleration. Alright, so let's solve for the formula. Here we go. How will we manipulate it to isolate the A? Well, first I'm going to move the VO over on this side. Next I will divide by 2 and divide by the displacement so I can isolate the A, which is our acceleration, giving us our formula, so it would be this. In an AP test again, the question, they rarely ask you, okay, can you plug in the numbers and solve? They mainly ask you, what formula would you use to solve for it? So here you go. If you had given this one, they would have not given you points, and you're like, what's wrong with it? Well, it's solving for velocity, final. They wanted the acceleration. Oh, so you got to isolate whatever that they're looking for. Alright, so keep that in mind. Now that we have the formula, let's go ahead and plug it in, the values, and solve for the A. So acceleration on the x-axis is equal to the velocity, 30 meters per second, and that is squared, minus the initial velocity of 20 meters per second, squared as well, and 2 times the displacement, which was 200 meters. Okay, at this point, you go ahead and plug it into your calculator, so it would be 900 meters squared per second squared minus 400 meters squared per second squared over 2 times 200 will give you 400 meters. So our acceleration will be 900 minus 500 will give me 900 minus 400 will give me 500 meters squared per second squared over 400 meters. So our answer for part A is 1.25 meters per second squared. Alright, that takes care of part A. In part B, they go ahead and they ask you guys, find the time it takes the boat to travel the given distance. Okay, so we're going to go ahead and do that. The acceleration is 1.25. I'm going to write it here with the given because we're going to need it to solve the next part. Alright, to solve for the acceleration, for the time, time, we're going to go ahead and use this formula. Why? Because we have the velocity, initial and final, and we have the acceleration now that we've solved for it in part A, so we can use that to solve for the time. Alright, so look like this on the x-axis. Move the v at time 0 over, and that's going to give us this, and I want the time, so I'm going to divide by acceleration on both sides, giving me time is equal to Vx minus Vxo over Ax, and there we have it. Alright, now that's the formula I'm going to use. Let's go ahead and plug in the numbers to get how much time it took to go from 20 to 30 meters per second. So time, velocity was 30 meters per second minus 20 meters per second divided by the acceleration, 1.25 meters per second squared. So that's going to be 30 minus 20 is 10, and then 10 divided by 1.25, it gives us 8 seconds. That was part B. That would be the amount of time it took to go from 20 meters per second to 30 meters per second. Alright, part C. They want a velocity time graph of this problem. So part C will look like this. Time always on the x-axis. Velocity, we'll put it here. Let's see, 0, we'll put 10 over here, 20 over here, 30 over there. And time 0, 8 seconds. Move it over a little bit. Time in seconds. Put velocity in meters per second. And over 8 seconds it went from 20 to 30, so that will be our velocity time graph. Here's velocity time, there you go, from 20 to 30 in 8 seconds. Alright, that takes care of problem number 9. Up next is problem 10. In this problem they ask you, an athlete is sprinting southbound at a constant velocity of 8 meters per second for 10 seconds. Then the athlete begins to slow down until becoming at rest, which takes about 5 seconds. Once at rest, the athlete immediately turns around and begins to accelerate over a period of 5 seconds until you reach a velocity of 8 meters per second. The athlete runs at 8 meters per second for 10 seconds. Alright, then the question number, or letter A, draw a velocity time graph for the athlete. So let's go ahead and do that. Alright, in this graph I have here 8 positive, and that's going to be in the southbound direction. So I'm going to put the positive in the south. North, we're going to leave it as negative. And here's our velocity. So I have a velocity time graph. It's 8 meters per second for 10 seconds. So here's my time, 10 seconds. So the athlete ran at a constant velocity. So that means the line will be flat for 10 seconds. Alright, then they describe it. The athlete begins to slow down until coming to rest. That means that the velocity is 0 and it takes 5 seconds. So from 8 down to 0, it takes 5 seconds. So here's 10, that's 15. So my line will look like that. Alright. Next, the athlete turns around and begins to accelerate over a period of 5 seconds until it reaches a velocity of 8 meters per second. Alright, so again it's going to take 5 seconds to reach 8 meters per second. And if you're wondering why is the line on the negative side, the answer for that is because the athlete turned around, so now it's going in the other direction. Alright, once he reaches that speed, the athlete runs at 8 meters per second for 10 seconds. So from 10 to 20, that's your extra 10 seconds at 8 meters per second. And there we have it. So in A, draw a velocity time graph. That would be your answer for A. Now let's move on to part B. Part B, they ask you guys, what is the acceleration of the athlete while they are slowing down? So from here to there. There's a couple of ways you can solve for it. In a velocity time graph, the slope of the line is the acceleration of an object. So if you get the slope of this line, then you can go ahead and have the acceleration. So I'm going to go ahead and do that. Acceleration is, let me get rid of the symbol, acceleration equals the velocity final minus velocity initial, time final minus time initial. So that's just like the slope formula, and that will give you the acceleration. So time final, while it was slowing down, was 0, minus velocity initial was 8 meters per second. Time final was at 15 seconds, and initial time, when it started deceleration, was at 10 seconds. So that's going to go ahead and give me negative 8 over 15 minus 10 is 5. So 8 divided by 5 gives me 1.6, negative 1.6 meters per second squared. And if you're wondering about the negative sign, well, our athlete is slowing down, so therefore they have negative acceleration. So that's one method of solving that problem, solve for the slope of the line that you're asking about. The other one, let's go with the lesson that they're teaching us. They brought up these formulas, so let's go ahead and use it. Alright, so it's going to be the acceleration, Vx equals Vxo plus acceleration on the x-axis times t. We want the acceleration, so we're going to go ahead and move over the Vxo by subtraction. And then we're going to go ahead and divide it by time on both sides. And there's our formula. So the acceleration is equal to Vx minus Vo over the time. So let's plug in the numbers. Acceleration on the x-axis. The athlete, when they began to slow down, they came to rest, so that's 0. And the initial velocity was 8 meters per second. And then time. How long did it take the athlete to slow down? That was 5 seconds. So the answer is the same value, 1.6 meter per second squared. So you end up with the same value for the answer as before. So whether you use this formula on top or the slope formula in a velocity time graph, either one will give you the same answer. Now let's go ahead and move on to part C. In part C they ask you, what is the displacement of the athlete? So how far did they travel? Now remember that displacement is the distance from the origin. So they began here, and how far did they travel? Okay, the answer for this one, if you look at the graph, the answer is 0. How far did they go? They did travel in one direction at first, but then they turned around and came back. So therefore, the answer for letter C is 0. They did not travel. Having said that, let's go ahead and put it mathematically to make sure. Alright, so one of the things that we've learned is also the slope of the line is the acceleration in a velocity time graph, but also the area under the line, that is the displacement in a velocity time graph. So we're going to go ahead and look for the area for this square. We're going to call that part 1 for the triangle, this triangle, and that rectangle, I should say. Alright, so when you have constant velocity, displacement is equal to velocity times time. So for part 1 and part 4, all you have to do is get velocity times time. So let's do that. Part 1, it's equal to velocity, which our athlete was traveling at 8 meters per second, and they did so for 10 seconds. So that gives us 80 meters. Part 2, Oh, you have an acceleration. In this case, negative acceleration. They're slowing down. That is, for the displacement, it is a triangle. So 1/2 base times height. Base is the time, and the height is the velocity. So for part 2, it will be 1/2. Let's see, the velocity was 8 meters per second, and they decelerated over 5 seconds, so that gives us 20 meters. Part 3 is the opposite. It is 1/2. Notice the velocity is a negative 8 meters per second, because they're going in the other direction, over 5 seconds, so that gives us a negative 20. And finally, part 4, it's just a rectangle, so there's no acceleration here, so it's just velocity times time. Alright, so it's going to give us negative 8 meters, because they're going in the opposite direction, over 10 seconds, 80 meters. Put it all together, 80 plus 20 is 100, minus 20 minus 80, for a grand total of 0 meters. They went back to the origin, so the displacement is 0. That is problem number 10. Problem number 11, I could best describe it as a true AP style question. In it, they don't give you any numbers, they just want you to solve the problem using just symbols. Alright, so let's go ahead and get to work on this one. It says, a car starts from rest and travels for t1 seconds with a uniform acceleration of a1. So the first part of the journey, this is the information that's given us. Now, then it says, the driver then applies the brakes, causing a uniform acceleration a2, so that's a negative acceleration. If the brakes are applied for t2 amount of time in seconds, how fast is the car traveling just before the beginning of the braking period? So I went ahead and went with a graph right here. So at first the car accelerates very quickly, then it immediately begins to decelerate. A1 and A2, the acceleration before, while accelerating and decelerating are not the same, so therefore my triangle is not supposed to look the same on both sides. The amount of time is not given to us, and we should not assume that they're the same, so again I made them different lengths. Maybe they could be, but maybe they could not be. The velocity, the original velocity at times 0 for the first part of the journey is 0. It starts from rest, and it goes up to the velocity for the first part of the journey. I label it as V1. Now, treating this as a separate part to the problem, and then we'll add them together, we're going to go ahead and get VO2, which is the original velocity at the second part of the journey, is the same as V1. And we're going to go ahead and plug it in, and V2 is at 0 right here. Alright, so now we have that. Let's do part A. In part A, they ask you, how would you solve for the velocity of the car? So we're going to do that. V1, what would it be? So V1, it's equal to VO1 plus the acceleration 1 times time 1. Now, in this problem, that's what we're solving for. We should simplify it slightly. We know that VO1 started from rest, so that's a 0. So my answer is going to be, well, if you want velocity here, it's going to be just the acceleration 1 multiplied times time 1. And that would be your answer for part A. Alright. Now part B, they go and they ask you, how far does a car go before the driver begins to brake? So the distance. Now they want the distance for this. Here we go. We're going to go ahead and use this formula to get the distance. Though we could also use this one on top to get the distance as well. Alright, so let's use this formula. It's a little bit simpler, so let's go with that. So for part B, they're going to have, what is the displacement for the first part of the journey? So I'm going to put the 1. The original velocity times time plus 1/2 the acceleration 1 times time 1 squared. Alright, now I want to point out that VO1 is a 0. So 0 times 10 will give me a 0. So again, this is going to cancel out. So the answer for how far we would travel for the first part of the journey is 1/2 A1 multiplied times T1 squared. So that would be your answer for part B. Alright, part C. It says, using the answers from A and B as the initial velocity and position for the motion of the car during the braking, what is the total distance of the car? Alright, so we do have the first part of the journey, that's a distance for this section. They want to know, hey, what's the distance for that journey right there? Okay, so let's go ahead and solve for that. We're going to go ahead and use this formula again, but remember it's for the second part of the journey. So it's going to look like this. Second part of the journey is VO2 times time plus 1/2 acceleration 2, which is the negative acceleration to get the car to brake, and the amount it took 2 squared. Alright, so that's the formula that we're going to use, and there is a bit of a problem because in these AP style problems they only want you to use what they've given us. So they gave us that, they said it was at rest, they gave us that. They never give us that, so we cannot have it. It cannot be part of the formula. Alright, so what do we do then? Well, I want you to notice that you see this line and that line meet there. So V1 equals VO2. This is the same. So we're going to go ahead and replace it with that. So it's going to be V1 goes right here, since the ending spot of the first part is the beginning spot of the second part. So I'm going to substitute it. Great. So that's how we'll get it. Now, if you're sharp eye, you might also have pointed out, it's like, yeah, but we also didn't get V1 in here either. We have VO1, but not V1. Alright, so then what do we do then? They gave it away right there using part A. We're going to substitute. We know what V1 is. It's A1 times T1. So this would be the actual formula that they would allow us to use during the AP test for credit. Because you see, we do have all of these. Whether that was T2, I neglected to put that. We do have all of these were given to us. So V1, we got V1 here, and VO2 is the same as V1, so that's why I could substitute there. Alright, now they wanted the total distance. This only gives us a distance for the second part. So how will we get the total distance from here and there? We'll add them together. So we do have both pieces, and all we got to do is just add them together, and that's it. I'm a little bit out of space, so I'm going to erase my graph to give me some space right here. So I'm going to get the total. Alright, so the total displacement would just be from the first part plus the second part, right? So we're gonna write the first one right here. That's x1. We're gonna go ahead and put it down. So for our total, it's gonna be 1/2 A1 times time 1 squared plus this part, which is A1 times T1 times T2 plus 1/2 A2 times T2 squared. And that would be the answer for an AP question, all letters, no numbers. Up next, we're going to move on to free-falling objects. In this lesson, we're going to look at the acceleration due to gravity. The value for it is 9.8 meters per second squared. Though for our calculations, we will end up using 10.0 rather than 9.8, just to make our numbers a little bit easier and more manageable. So up here, a free-falling object is any object moving freely under the influence of gravity alone. Free-falling object acceleration, also known as g, on a planet Earth is 9.8 meters per second squared. Now, free-falling means nothing else is affecting it. When a skydiver jumps off from a plane and they're falling. They're not truly free falling, and the reason why they're not is because there is air resistance that they're experiencing. And you can definitely see that when they open their parachute, and the parachute creates a lot of drag from that air resistance, which slows them down. So air resistance really inhibits free falling. Also, the shape of an object will affect it, again, if there's air. Perhaps if you think of a balloon filled with water versus a balloon filled with air, and you drop them, they're not going to fall at the same rate because of buoyancy. And that, once again, that's air playing a role in how fast they fall. So free falling is with no air. Now, a lot of the problems we're going to look at, they're all on planet Earth. Ideally, we should be doing them on somewhere where there's no atmosphere, and like the moon. But to keep it more realistic, we're going to look at planet Earth, and a lot of the time we'll end up ignoring air resistance. And the problems that actually stated ignore air resistance, because yes, it plays a role, it will affect it, but it's small, so we're going to ignore it. Alright, so now let's go ahead and take a look at a problem. Oh, actually, I should mention the picture here. If you look for the video, here's the astronaut. I forgot his name. He's holding a hammer on one side and a feather on the other. And because there's no air, there's no atmosphere, he can drop them and they both fall at the same rate, because all objects are pulled towards Earth at the same rate, which is 9.8 meters per second square. But again, we're going to use 10.0 for our calculations. Let's take a look at example 6. In this example, it says a ball is thrown from the top of a building with an initial velocity of 20 meters per second straight upwards. So there's our objects being thrown up. This individual where the ball is being released is at a height of 50. So, but we're going to say that right there the object is 0. The original height right there is 0. So that's our starting point. And so therefore, from his hand going down, that'll be negative 50 because it is dropping. Alright, and they're 50 meters above the ground. And part A, they're going to ask you to determine the time needed for the ball to reach its maximum height from here to there. Now, not given to us, but we got to assume is how fast, as the ball's rising, how fast is it going when it reaches the apex, the top? The answer for that is it's going to go up, 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 and then stop right there. It reaches a velocity of 0. So that's implied. So our velocity original at time 0 on the y-axis, now we're going to be looking at the y-axis because it's up and down, is 20 meters per second. And positive because we said up is positive. Alright, and final velocity on the y-axis is 0 once it reaches the top part at that moment. Okay, next. What else is given to us? We're 50 meters above the ground, but that's irrelevant to this section. But very important to us, acceleration on the y-axis. There is an acceleration acting on it. It's gravity. It's pulling down on the object. It's pulling down. That means we're going to give it a value of negative 10 meters per second squared. We said it was 9.8, but to keep our calculations simple, we're going to go with 10 meters per second. Alright, and one more time, the question is how much time is needed for the ball to reach that apex? So time. Alright, so here's our formula. We're going to replace those x's with y's because we're no longer in the x-axis, we're on the y-axis. So let's see, Vy, it's equal to Voy plus acceleration on the y-axis times time. We want to isolate the time, so we're going to move this Voy over to this side, so we end up with this, Vo minus Voy. It's equal to acceleration on the y-axis times time. And then we want to isolate the t, so we're going to divide by the acceleration on both sides, giving us the time. So there's a formula for it. Now you could probably simplify this a little bit further by saying, well, velocity at the apex is 0, so could I get rid of that? Sure. And they might do that also in the test where they'll simplify it and have a value that is 0. It just won't even be present. So there's your answer. The negative comes over. Alright, now time will always be positive. Negative time means you've dropped a sign somewhere, or you're time traveling, which is not allowed in physics class. No negative time. So if you're wondering, but we have a negative there, or our acceleration is negative because the earth is pulling you down in the negative direction. So that's going to give us a positive value for the t. Alright, let's plug in the values. This was 20 meters per second and 10 meters per second squared. And that is the time. So the answer for time will be 20 minus 10, 2 seconds. That is part A for this problem. Up next, in part B, they ask you, calculate the maximum height. How far up did this object travel after it was thrown up at 20 meters per second up? Alright, so we want to get the displacement. We do have the displacement, we have the acceleration due to gravity, we also have the velocity initial and final. Alright, so we can use that to solve for it. We do have the time and the acceleration and the initial velocity, and so we can also use the top formula, the middle formula to figure it out. Let's go ahead and use the middle formula to figure it out. Instead of x's though, because we're on the y-axis, and I'm going to go ahead and put y's. So here's our formula. So displacement on the y-axis for going from here to the apex right there is going to be equal to the displacement on the y-axis original plus 1/2 acceleration on the y-axis times time squared. And pardon me, I left out a time. Alright, so here we go. Alright, so there's our formula, and we do have the time, which we solved in part A. So let's go ahead and solve for this one. What is the displacement on the y-axis for that first part? Initial velocity, it was thrown at 20 meters per second. The time that it traveled, it was 2 seconds to the apex. Acceleration, it's negative 10 meters per second squared. That's gravity pulling down on an object. And our time, it was 2 seconds, and that is squared. So that is our formula. You go ahead and get your calculator and you solve for it. Let's see, it's going to be 20 times 2, that is 40 meters. And on this side, it's going to be 2 squared is 4, 4 times 10 is 40, times a half is 20. Notice the negative because of the negative on the 20. So our answer is 20 meters. That is the answer for from where the object was launched to the apex. It is 20 meters above from the object when it was thrown. Compared to the ground, if the ground is 50 meters away, 20 meters above that would be a grand total of 70 meters. So that is for the first part of the journey, it's 20 meters above the ground. Alright, in part C they ask you, what is the time needed for the ball to return to the beginning height from which it was thrown? Alright, so that one is L1. They also want the velocity at that instant. That one is a pretty easy one to get. If it took 2 seconds to go up, it's going to take 2 seconds to go down. So how much time did it take to go up and come back down? 2 seconds up, 2 seconds down. So for that part of the journey, so for part C, I would say 4 seconds. Because it was 2 seconds to go up, 2 seconds to go down, add them up, there's your 2 seconds. Alright, if this person released the object at 20 meters per second up, so what would be their velocity on its way down? Because they also want the velocity at the instant it comes down to where it was released. The answer is negative 20 meters per second. Why negative? Because it's going in the downward direction, and downward is negative. That's part C of this problem. Let's take a look at part D now from the problem. In this time they ask you, what is the time needed for the ball to reach the ground? Now this problem is from the origin when it's thrown up at 20 meters per second all the way till it reaches the ground. Alright, so that's what we'll be looking at. And in this problem, we're going to go ahead and take a look at this equation to get the displacement, because we have the acceleration through the earth, and we're going to go ahead and we have the velocity going up, and that's going to give us the velocity right before it reaches the ground. And once we have that, we can go ahead and plug it in here to get the time. That'll be the easiest way to solve it. We could go this way because we do have the acceleration and initial velocity of 20, and so for the t, and the height was 50, so we could go that way, but that would lead us towards quadratic formula. So instead, let's just go ahead and use the second formula, the third formula, to solve for velocity. Once we have it, you can plug it here and solve for the time. Alright, so let's go ahead and start. How fast is this object right before it hits the ground? So we're going to start with the velocity original, which was 20 meters per second, plus 2 times the acceleration. The acceleration, which is 10 meters per second squared due to gravity. And the height, remember that this is 0, so that is below, so that is negative 50 meters. Alright, so go ahead and start using a calculator. 20, and pardon me, that is squared, as you see right there. So 20 squared, that gives us 40 meters squared per second squared, plus negative times a negative will end up giving us a positive. 50 times 2 is 100, times 10 is 1,000 meters squared per second squared. The meter squared comes from the multiplication of both of these meters. And then after that, we add them up. So, pardon me, I wrote 40 there. That should be 400. Multiply both, add both of these, so it gives us 1,400 meters squared per second squared. And then we get the square root, and that will give us the value that we're looking for. And square root of 1,400, 37.4 meters per second. And that, by the way, I do have to point that it is going down in downwards direction, so I'm going to put negative to show that it is going in the downward direction. Alright, so now that we have that, we can go ahead and get this value. We know the final velocity now. We know that the original velocity was 20 upwards, so we're going to use that to solve for the time. So that is negative 37.4 meters per second. It's equal to the velocity, which was initially 20 meters per second, plus the acceleration on the y-axis, which is 20 meters per second, 10 meters per second, times time, which is what we're solving for. I'm going to subtract both sides by 20. That's going to go ahead and give me negative 57.4 meters per second. It's equal to 10 meters per second squared times time, negative 10. So we're going to go ahead and divide both sides by the acceleration. That cancels out, giving us a time of 5.74 meters. Oh, nope, sorry. That got canceled out. Seconds. Meters and the seconds got canceled out, leaving only 1 second, so there it is. That is the total amount of time for the journey in part D. Alright, now let's go ahead and take a look at part E. In this problem, it says the velocity and position of the ball at 5 seconds after it has been launched. Alright, so for the velocity, let's start with the displacement. How far down is it? This object, so we're going to use this formula right here. And where is this ball? Velocity originally was thrown up. So I'm going to put positive 20 meters per second. And time is going to be 5 seconds. Next, going to be 1/2 the acceleration due to gravity, which is negative 10 meters per second squared. Multiply times the squared of the time that is in flight, and they told us 5 seconds. So after 5 seconds, where is this object? So we go ahead and get our calculator, start plugging in. 20 times 5, that'll give us 100 meters. And the negative, that's going to end up giving us a negative right there. 5 times 5 is 25. So, I'm going to need my calculator for this. 125 meters. Alright, and we subtract, so we end up with negative 25 meters. Alright, what does a negative 25 meters mean? Remember that where the object was released, we said that's the origin, so it is at 0. So negative 25 means that that object at 5 seconds is about halfway down the building. So that will be more or less where it is. They also asked us to find not just the position but the velocity. how fast is this object traveling? So we're going to go ahead and use the top formula. Alright, and for that one, let's see, how fast is this object traveling? We're going to go ahead and have 20 meters per second, and add plus negative 10 meters per second squared, and that's going to be 5 seconds of travel time. So the velocity is going to be, multiply both of these, notice that's a negative, so we're going to end up with 20 meters per second, because remember that's the initial velocity when it's thrown up, so that's why it's positive. 10 acceleration due to gravity times the time, so that's a negative 50 meters per second. So that's going to give us a velocity of negative 30 meters per second. And again, why negative? Because remember, at this point, it is traveling downwards, so that's why it has a negative value for the velocity. That takes care of part E. Let's go ahead and move on to part F of this problem. Now in this one they ask you, can you draw a position time graph, a velocity time graph, and an acceleration time graph for this object? Alright, so we're going to go ahead and represent them in graphs. Let's start with the position time graph. So we're going to have, here's going to be the y-axis, and we're going to have here be the t for time. Let me put it at the origin, which was further up here, t for time. Alright, so this is 0. It will look like a parabola going down. So that will be our position, change in position. First it went up, then it came back down and passed the origin all the way to the ground. So that would be a position time graph for this example. Next, the velocity. For this one, the velocity time graph would look like so, more or less. It does have an initial velocity of 20, and if this is 0, so we would start somewhere above 0 at 20, and then it would go down to 0. That would be this point right here, and then we'll keep on going down, down, down. Now it's negative, 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 as it's moving downwards. Finally, the acceleration time graph for this problem. So here we have our acceleration. Let me move it up here. Where would you put it? Remember, the only source of acceleration is the Earth pulling down, and it's pulling down is negative, so I'm going to put a line about here. As long as it's below the 0, it should be at negative 10, but I don't have any digits there, so that's pretty good. So that'll be your position time graph, velocity time graph, and acceleration time graph for problem, for this example, example 6. Up next is problem number 12. In problem number 12, they talk to us about a rocket. It says a rocket moves straight upwards, starting from rest, with an acceleration of positive, since it's going up, 29.4 meters per second. It runs out of fuel after 4 seconds, and it continues to coast upwards. So it has that acceleration here. Once it runs out of fuel, it still has momentum, so it's going to carry it up, up, up until it reaches an apex, and then it's going to come back down. Alright, reaching the maximum height before falling back to Earth. In part A, they go ahead and they ask you, find the rocket's velocity after 4 seconds. Alright, so we're going to go to, let's write down what is given to us. And there's really 2 parts to it. In part 1, when the rocket is on, it has an acceleration. And the acceleration is positive 29.4 meters per second. That is our net acceleration. Alright, and it travels for 4 seconds. After that, it turns off. After the boosters turns off, there's only one source of acceleration. That is Earth pulling down on it. So this will be a second part of our journey. Put 1 and 2 here, and that will be 10 meters per second squared. Alright, that's the only force acting on it, is force of gravity pulling down on our rocket. But for the first part, they want to know, what is the velocity when it reaches 4 seconds? Right before the instant the engine cuts out, what is our velocity? So we're going to go ahead and use this formula right here. So we'll put y because we're on the y-axis, Vyo plus acceleration on the y-axis times time. Alright, now the rocket does start from rest. So we know that Vyo is 0, has no value. So I'm going to simplify the formula a little bit, which is acceleration times time, and that's going to give us our velocity. The acceleration was given to us, 29.4 meters per second squared. And time, it was 4 seconds. So you go ahead and you get a value of we're going to round it up slightly to 118 meters per second. That is part A. Find the velocity. Find the velocity and position. Alright, so we got the velocity. Now what is a position? How far up is this rocket? That's next. So on velocity and position, and this will be part A. So to get that, let's see. We could use this formula here, or we could use this formula as well. Either one will work out, because we do have the acceleration, we have the time, and initial velocity was 0. And you know what? Let's use that one. It looks a lot simpler, so let's go with that. So I'm going to put it for the y-axis because we're going up and down, so you'll see me replace all those x's with y's. Alright, so how far up did it travel? So what's the change on the y-axis? And we know that this is a 0, so VYO, the rocket started from rest. So it's at 0. 0 times time is 0. So I'm going to simplify the formula to that. So that's going to be our formula to solve for this problem. Alright, let's plug in the numbers. So it's 1/2 the acceleration, which was 29.4 meters per second squared, multiplied times the time, which is 4 seconds squared. Alright, so plug it all in. And we go ahead and we get a height of 235.2 meters. So we got the position and the velocity of this rocket. That is part A of this problem. In part B of the problem, they go ahead and they tell you guys, find the maximum height of the rocket. Now remember, that maximum height is broken up into 2 parts, when the boosters were on and when the boosters were off. So we're going to get 2 different accelerations. Alright, so so it's essentially solving 2 separate sections. We know from the start to where the boosters go off, we already climbed 235 meters. We know that from part A. Now in part B, let's go ahead and figure out how much it actually climbs. So we're going to go ahead and use this formula right here. Alright, now the original velocity when the boosters turn off then is this right here. We got it, 118 meters per second. So we're going to go ahead and then think about this. It climbs all the way up to here. And what happens at the apex? How fast is it climbing? The answer at the apex is 0. So this value, the final velocity is 0 at the apex. So let's go ahead and use the formula to solve for this. And all of this is on the y-axis. Alright, so let's go ahead and move this over. Next, I want you to remember what I said. This one was 0, so we can get rid of it. And so you won't see it anymore. And then we're going to divide by 2 and the acceleration, so we can have the answer for what is the distance. For this is for the second part while the boosters have turned off and when it reaches the top. That's the distance. So I'm going to label this one as part 1 of the journey and this one's part 2 of our journey. Alright, so let's plug in the values. When the rockets turned off, we were traveling at 118 meters per second. And there's only one force acting on it, the acceleration due to gravity. And because gravity is pulling you down, you'll see me put that negative in it. That's going to cancel with that one, so we're going to end up with a positive height for the second part. So that's going to go ahead and be 118 divided by 20. So, oops, pardon me, I missed something. The square there. Alright, so notice I left that out. So, you gotta redo those calculations. 118 squared divided by 20. And it's gonna go ahead and give me about 696 meters. And that's for the momentum from the time the booster's turned off all the way to reaches the apex. Alright, so now to get the grand total, I'll put y with a t right there for total. Well, I'm going to say, well, it's y the first part of the journey while it was with the boosters on, plus y second part of the journey, which is the boosters off, but momentum carries it all the way to the apex. So that'll be 235 meters plus 696 meters. So our grand total for part B, which is how high up did it travel, 931 meters, give or take. Alright, so that is part B of this problem. Alright, up next, let's go ahead and work on part C. Find the velocity the instant the rocket crashes the ground. So it is just a hair from crashing into the ground. How fast, what is the velocity of this rocket? Alright, for that calculation we're going to use this formula here because we have the total height that it traveled, right? So from here down, we know that going down, only acceleration from Earth is acting on it, and at the apex the velocity is 0, so our starting velocity is 0. So we're going to go ahead and use those values to help us solve for that. So the velocity on the y-axis squared, initial plus 2 times acceleration on the y-axis times the distance traveled on the y-axis total. That's going to be our formula. That is a 0 because at the apex the rocket's no longer moving up or down. As soon as it reaches the apex, is therefore a no velocity for a fraction of a second. So that's gone. So it's just really this. 2 times acceleration due to gravity times the total height. Alright, so we plug in those values. 2 times negative 10 meters per second squared multiplied times the height. It was at 931 meters. So it's going to go ahead and multiply all of these. So it's going to be 931 times 10 times 2 gives us 18,620 meters squared per second squared. Notice the negative, negative. Alright, I need to get rid of that square root right there. And so we're going to go ahead and square root it to get rid of the square. That's going to give me Vy. And at this point, your math teacher in your head is going like, wait a minute, negative, square root, that is a problem. Now we're going to get imaginary numbers. But I want you to take a moment to remember that in physics, the positives and the negatives are merely pointing to directions. So I'm going to erase it and we'll put it back at the end. Alright, again, those positive and negatives are telling you are we going up or down, but the value is going to remain the same. So square root of our answer, it is 136 meters per second, and the negative again just means that it's going that fast, going down. Again, our negatives are just directions, so don't get too hung up on the fact that, oh no, imaginary numbers in a radical, don't worry about that. Alright, so that is part C for this problem. That also brings us to the end of our lesson on acceleration, one-dimensional motion, and falling objects. Thank you for watching.